Hello everyone, and welcome to Looking for Pythagoras 2.3. Our learning target for this part of the investigation is that we want to be able to use the areas of squares to find lengths of sides. And what we're going to do is kind of tie together everything that we've been working on so far and looking for Pythagoras, and hopefully make some sense of why we did some of those things with the different shapes and drawing rectangles around them. Now we're going to use it to find side lengths of squares. So as it tells us here that we can use a square to find the length of a segment connecting dots on a grid, or if we don't have 5 dot by 5 dot grids, then you can use coordinate grids, just regular graphing paper, if you'd like to do that, or if that's what you have available. So it says, for example, to find the length of the segment on the left, over here on our left side, it says draw a square with the segment as a side, which is what they do here. But in order to do that, because you're not already going to have the square drawn, remember that the slopes of parallel, this means parallel, not slopes of 11 lines, this is slopes of parallel lines, are equal. Also, the slopes of perpendicular, remember this is a sign for perpendicular, slopes of perpendicular lines are opposite reciprocals. So that's how we could tell if our slopes were accurate or not if we are going ahead and doing this ourselves. Instead of having the box already drawn, we can find the slope of this line. Our change in y from here to here is 1, and our change in x from here to here is 2. So our slope with this would be 1 over 2, which means to draw the lines here are perpendicular lines. We would want those to be a -2. Okay, a -2 or a -2 over 1 in fraction form. If you do that, you're going to wind up with this shape here. In the essence of time, I won't go ahead and do that for you, but let's go ahead and draw the rectangle around it like we did for other shapes earlier in this investigation in order to find the area. Well, if we do the area of this larger square, we get it's a 3 by 3 square. And remember, the area of a square equals the side length squared. So our side length is 3. I'm trying to do this right-handed when I write left-handed. Okay, equals 9. Okay, so our area of the big square is 9. Now, we need to take out the area of these triangles. Remember, the area of a triangle equals base times height divided by 2 or times 1/2, whichever you prefer. So each of these is a 2 by 1. So 2 times 1 is 2, divided by 2 is 1. So we would go ahead and take out 1 unit for each of these. So then we take our original area of 9, we subtract out 4 for all of the triangles, and we wind up with 5. So that means that our area is 5. Okay, area is 5. And if we want to be able to find the side length, then side length equals the square root of area. So if we go ahead and take the square root of this and the square root of our side squared, which is our area, okay, we wind up with messed that one up. We wind up with side length equals square root of 5. Okay, so that's just tying together everything that we've done so far in this investigation, investigation 2. So we found out that this side length is exactly the square root of 5 units. So now for you to work on some of them, it says on a 5 dot by 5 dot grids, draw line segments with as many different lengths as possible by connecting dots. Label each segment with its length. Use a square root symbol to express lengths that are not whole numbers, as in anything that we have going diagonally is going to have some sort of square root side length. Any of these that we have going across, like that's going to be 1, or if we had it going up here, that's going to be 2. But those going diagonal are going to be some sort of square root. Now, if you don't have the 5 dot by 5 dot grids, again, just use regular coordinate grid paper, graph paper that is set up in a 5 by 5 area such as this. You can just mark off a 5 by 5 area as you need. I want you to do 1, 2, and 3 here in part A. Part 2 is list the links in increasing order and then estimate each non-whole number linked to one decimal place. That means without a calculator. If you're estimating to one to a non-whole number linked to 1 decimal. That's without a calculator. Then part B. Part B, Ellis says the length of the segment in figure 1 is the square root of 8 units. Okay, you can go ahead and use our same square thing that we did to determine the length of this segment. Oscar says it is 2 times the square root of 2 units. Are both of the students correct? And explain how you would be able to know this or be able to prove that it is or is not correct. And then finally, once you have the understanding of that, then we're going to try number 2, express the exact length of the segment, this segment in figure 2 in 2 different ways. Okay, so as in here, there's a square root of 8, and somebody else says it's 2 times the square root of 2. If you can prove that's true, then we should be able to list this in 2 different ways as well. So get through A and B there, and then if you still have time, go ahead and start working on these ACES questions beginning on page 30. Hope you enjoy it. Let me know what questions you have, and show me your proofs by the end.